Every year, thousands of patients receive metal implants to support broken or damaged bone, but metal does not degrade. It must be surgically removed once healing is complete. This project asks a simple question: what if the implant could dissolve on its own? Titanium and steel implants are strong but permanent. Removing them requires a second operation, additional cost, additional risk, and a longer recovery. Cancellous bone, the spongy bone found inside our joints, only needs a compressive strength of 1.5 to 45 megapascals to support healing. A range of biodegradable material could realistically match. Our project explores PLA/wood fiber composite, a biodegradable wood-based 3D printing filament, as a scaffold for cancellous bone. It is strong enough to support the healing process, and it breaks down naturally afterward, removing the need for a second surgery. 3D printing introduces variables that directly affect performance. We focused on two: infill density, the amount of material inside each part, set at 30% and 70%, and infill pattern, comparing line and gyroid. Our objective was to determine which combination offers the best balance of compressive strength and biodegradability for a bone scaffold. We designed a standard test cylinder in AutoCAD in accordance with ASTM D695, converted it to an STL file, and printed it using an Elegoo FDM 3D printer. Using a full factorial design of experiment, we produced 8 samples. Every combination of infill density and pattern replicated twice to ensure our results were statistically reliable. Each sample was printed at a nozzle temperature of 220 degrees Celsius and a bed temperature of 60 degrees with a layer height of 0.2 millimeters. Every sample was labeled by its parameters and visually inspected. Any print with visible defects was discarded and reprinted. First, we evaluated compressive strength. Using a universal testing machine, we measured how much load each sample could withstand before failure. The strongest result came from 70% infill density with a line pattern, reaching 56.2 megapascals. Every combination we tested exceeded the minimum strength required for cancellous bone. Second, we evaluated degradation. Each sample was immersed in a pH 5 buffer solution at 37 degrees Celsius, simulating the human body, and weighed at regular intervals over 21 days. The fastest degrading sample, 30% infill density with a line pattern, lost 3.65% of its mass, confirming that the material degrades under physiological conditions. We then ran an analysis of variance, or ANOVA, to determine which factor had the greatest influence. Infill density showed a statistically significant effect on both strength and degradation, while infill pattern did not. In other words, the amount of material printed inside a part matters considerably more than the shape of that material. This gives clinicians a choice rather than a compromise. For maximum load-bearing strength, 70% infill is preferable. For faster degradation in patients who heal more quickly, 30% infill is the better option. Every combination tested remains a viable option depending on the specific needs of the patient. While this is a small-scale study, it points toward a meaningful direction. 3D printed wood-based implants that support healing and then degrade naturally, reducing cost, discomfort, and recovery time for patients. Thank you for your time.